Hey, Tyler.
Hey, Dr. Godes, we got a different angle going on today.
Right, exactly. A little obliqueness going on.
Yeah.
So welcome to the post-class video on rate laws. And rate laws are the description of how the rate changes with concentration. Increased concentration, increase the rate, generally. Now, as we found out in class, there's language associated with this. Zero order means
It's not dependent.
it doesn't depend on the concentration of that component. So you can change it all you want, you're not going to change the rate.
Right.
First order means there's a linear dependence.
Right. Like straight line.
Yep, you double the concentration, you double the rate, and then a second order dependence, you double the concentration. It's kind of like an exponential function.
Right.
Yep, you quadruple the rate there. Right, and so there really are two different cases of problems here. One is kind of simple types of cases where you can kind of look at the data. And again, remember, you can only determine rate laws through experimental data. Right, so I want to know what the order is for the NO and the O2. And I start and I compare the first experiment to the second experiment. And look, and this concentration's changing, and that concentration's changing.
Well, now we can't calculate it. Because now we have two variables, right?
Right. So one of the keys here is that the two experiments you compare, one thing has to stay the same.
Okay. So do we have that? Hey, we do. So if we're looking at experiment 1 and experiment 3, the concentration of oxygen stays the same.
Okay.
So we can use that to calculate it.
Right. So the concentration of oxygen is staying the same in 1 and 3, and O is varying, so we can examine how the rate depends on NO.
There you go.
So how much did NO concentration change there?
It looked like it doubled.
It doubled. What happened to the rate?
The rate did not double.
It didn't double. If it doubled, it would be 2.8 something, and it's not.
Right, so it looks more like it quadrupled.
Yeah,
which
it quadrupled.
would be more of a this kind of graph.
Right, so I can start to write my rate law. I can say rate equals some rate constant times NO, and now I know, I've determined that the power is 2. It's second order in NO.
Right, because that's what was changing. So now we want to find out what it is for oxygen.
So I look at 2 where NO is constant, and for 2 and 3, the NO is constant.
That in green. There you go.
Okay, and what happens? Oh, it decreases there. So I'm going to compare 3 to 2.
Right.
Okay?
So
3.
that's doubling.
It doubles, going from 3 to 2. What happens to the rate? So this doubles, that means it's first order. So
Right.
I can say, or Tyler can write out
There you go.
the O2 dependence.
Right. And you don't have to put O. Do you put O?
You don't have to put O1 there. If you put O1 there, you're not wrong. Generally, people just leave it off if it's 1.
Right.
If it's 0, they leave this whole thing off. Right? If it was 0 order, I would just write it as KNO squared.
Right.
But if it's 1, you don't put the 1 there, you just put the compound there. Okay?
All right.
So we're going to go to a more complex example.
Oh, great.
Okay, so here we have a little bit more complex problem. The balanced equation is a little bit more complex. We have a 3 there, and so we suspect that maybe the rate law might be a little bit different. I don't know. And then we have a bunch of experiments where we varied the concentration and measured the rates again. But there's a little bit of a problem. We did all right with these first 2 experiments. We kept one thing constant and changed the other, but we didn't double it. Right? Instead of doubling it, we changed it by a different factor.
Why would they do that?
Why would they do that? That's bad experimental design, and I'd be very upset with the person that actually did the experiment. But we can still do this problem. And what we need to do is use the relationship. If here's the rate law under conditions 1 for experiment 1, here's the rate law for 2, it should be the same rate law. M and N are the same, K is going to be the same. They have different rates, different concentrations, but we have all that information.
Okay.
And if this equals that and that equals that, then if I take the ratio of the 2, this divided by that should equal the ratio of this divided by that.
Right.
Okay, so what I do is I take the ratio of the two rates. So rate 1, okay, so I have the ratio of the two rates over here, rate for 1, rate for 2.
That came from here.
The k's are identical, so that's actually going to cancel. That's going to be 1. I have the concentration of the S2082 minus for 1 and for 2, that ratio, raised to the m power. That's how that mathematically works out. And then the ratio of the concentrations of the I minus for experiment 1 and experiment 2 raised to the m. Now, of course, this ratio is going to be 1. What's 1 raised to any power?
1.
It's 1. So that also reduces to 1. And so I have this ratio equals this ratio raised to the m power. And what we find, if we calculate that out, well, if you solve this, it's fairly obvious what m has to be. In this particular case, m equals 1. Okay, so now I know that's not just m, that's 1. It's not just m, that's 1. It's a rate law, it doesn't change.
Right.
So what about trying to find I minus? Is there anywhere where S2082 minus stays the same?
No.
No, there is not. It's always changing, right? But now that we know what m is, we don't have to rely on the fact that they're going to cancel out. We can actually plug numbers in there, knowing that m is 1, and get an actual value for that. So now I can actually pick any of these two pairs and solve, as long as it's not 1 and 2.
Right.
Okay, 1 and 3. And so I write down the ratio of the rates and put the concentrations over there. Okay, so now we have the ratio of the rates from 1 and 3. The k's, of course, are going to cancel. The ratio of the concentrations of S2O8. And now we know that that's 1. We already figured out that that exponent is 1, so this becomes just a number. The ratio of the concentrations of the I minus from 1 and 3 and are unknown. And so I can do a little bit of math to begin with.
Okay.
Okay? And so I cross multiply this a half. Half to the 1 is a half. Cross multiply it. I get 0.6667 equals 0.6667 to the n. So what is n?
Again.
Again, n equals 1. So our rate law is rate equals k times S2082 minus to the 1, I minus also to the first power. Right. So it turns out to be a pretty simple rate law, even though the balanced equation is a little bit more complicated.
Right. So if the person doing the experiment had just chosen good values,
we wouldn't have to do all this
it
math.
would have been really quick.
Yep. Right, but it's important, and sometimes in experiments you can't control the concentration that well. Sometimes you kind of are stuck with what you have. So it's important to understand how to do this mathematically, and it's not that complicated. You just have to be systematic about it. Pick something where one of the concentrations doesn't change, figure out the exponent for the other component, and then you can pull pretty much any two experiments and just plug in the exponent you know into this equivalency.
So really quick, why don't we have that, why does that 3 not matter? You know the 3 before the add ion?
Well, why does that not matter? Well, it turns out that when chemical reactions happen, they happen kind of one step at a time. Like two things collide and they react, and then something else comes in and reacts. And so what this rate law is actually going to tell us, and we're going to spend an activity on it, is that in the reaction, the step, the collision that actually controls this reaction, we don't have 3 iodides coming together. What we actually have is 1 S2082 minus coming together with 1 I minus. Okay. That's actually the molecular collision that controls how fast this reaction goes.
Right, so they can only happen one at a time. That's why we're not multiplying it by 3 or multiplying it by a third.
Yep.
Makes sense.
Okay, so just FYI, in case you didn't pick up, this is that challenge problem from the activity, right? So hopefully you tried this and actually knew how to do this, but if not, here's the solution for it. And if you tried it and got it wrong, well, maybe this will help you figure out what went on there. So hope this helps, and see you in class.